Hello, welcome to my channel. My name is Fran, and today I'd like to talk about the journey from classical physics to quantum mechanics and how this journey suggests that when you look at reality, the reality you look at changes. How what we perceive as stable, solid, and real is but an illusion, while what seems like a fantasy may actually represent a deeper reality. Modern scientists come dangerously close to ancient mystics. We've come full circle from superstitions and magic to empiricism and mathematical rigor, all the way back to illusions and a fluid and connected reality created by mind. Sir James Jeans, the famous English physicist, astronomer, and mathematician, once said, "The universe looks more and more like a great thought rather than like a great machine." And today we will explore this concept in depth. So classical physics began in the 17th century when pioneers such as Galileo Galilei, René Descartes, Johannes Kepler, and Isaac Newton advanced a new idea that through experiments one could learn about nature, and through the use of mathematics one could describe and predict it. Rational empiricism was born. It was effectively stated that if you knew all the positions and momenta of all the particles in the universe, in principle, you could predict how the universe would evolve forevermore. In other words, you could, in principle, predict the future. They envisioned a block-type universe where the future already existed. We simply didn't know what it was, as we weren't able to access all the necessary information about it. At the time, most scientists didn't fully realize what the price for such a predictable universe was. Think about it. If the future already exists, then your free will must be an illusion. You think that you're making decisions, but in actual fact, your destiny is pretty much set in stone, and there is nothing that you can possibly do to change it. So classical physics rested on 5 basic assumptions: reality, locality, causality, continuity, and determinism. In other words, that the world exists independently of those who observe it, that the only way that objects can be influenced is via direct contact, that the arrow of time points only in one direction from past to future and never vice versa, that there are no discontinuous jumps in nature, or that, in other words, the fabric of space-time is smooth, and finally, that things progress in an orderly and predictable way. So as we said, in principle, we are able to predict the future if we know all the starting conditions and causal links between them. Classical physics still works really well when trying to explain or investigate the observable world at the macroscopic level. In fact, it worked so well that in 1894, physicist Albert Michelson stated that basically everything that needed to be discovered in physics at that point had already been discovered. It could only be specified and confirmed by future discoveries. 6 years later, physicist William Thomson echoed the same sentiment by stating, "There is nothing new to be discovered in physics now. All that remains is more and more precise measurement." Now, the irony of that statement is that roughly 20 years later, the quantum revolution would take place, proving that measurement itself appears to create the reality that we observe, and that more than 90% of the universe is made up of dark energy and dark matter, of which we know next to nothing, and that all that classical physics held so dear, time, space, and matter, are but stubborn illusions, that reality itself may simply be a fabrication of the mind, and that mind may be the seat of a deeper reality. It all started with light. As Thomson stated, there are only 2 small clouds on the horizon of physics. They both refer to the properties of light. Well, those 2 small clouds eventually brought the classical worldview to its knees. One problem was that many physicists, including Isaac Newton, had postulated that light was composed of particles, while others assumed it was a wave. The second problem was that the so-called ultraviolet catastrophe, that when objects were heated, the intensity of the light produced was predicted to be proportional to the frequencies of the light, or in other words, to their color. These worked well at low frequencies, but it broke down at higher frequencies beyond, at ultraviolet frequencies and beyond. At these frequencies, energies were predicted to become catastrophically immense. And that in reality did not happen. The problem was resolved by German physicist Max Planck, or mathematician, I should say, who postulated that light comes in discrete energy packets, the so-called quanta. But there was one more problem involving the nature of light, the famous photoelectric effect, for which Einstein himself won the Nobel Prize in 1921. According to the photoelectric effect, if you shine a light on a piece of metal, electrons will be knocked out of the metal, but not all frequencies can do this. Not all colors of light can do this. There was a wavelength threshold below which the electrons were released. So a red light could not overcome that threshold. A blue light could. So the classical idea of light as a wave could not account or explain this observation, because presumably a very bright red light could carry more energy than a dim blue light. Einstein, reusing Planck's idea of the quantum, found that the idea of light as a particle, or as particles of discrete energies, could account for the photoelectric effect. Mind you, Einstein did not at first understand the implications of his own discovery. He thought of the quantum as a simple mathematical trick. Little did he know that he'd set in motion the next scientific era, the quantum revolution, which in time will bring into question his own theory of relativity. So, as impossible as it seemed at the time that that light could be a quantum or a stream of discrete particles, rather than continuous and indivisible like a wave, this one assumption about light solved all the problems, answered all the questions that scientists had about light up until that point: the photoelectric effect, the ultraviolet catastrophe, and so on and so forth. According to Einstein's theory, each particle of red light carries very little energy because red light has a low frequency, while each particle of blue light has higher frequency and hence more energy. So no matter how many particles of red light you use, you will not be able to displace electrons from a metal bar because the frequency stays the same. While one particle of blue light can achieve the quote-unquote impossible because of its higher frequency. So no matter how bright a light is, that will not change its frequency and its ability to alter the structure of matter, if you will. It's the frequency that makes the difference. In other words, the color of the light. So when proponents of the law of assumption say that it's not a trying process, what they mean is it's not through effort, it's not through force or even through sheer willpower that you will achieve the impossible. It's by altering the mental and emotional frequency. So let's go back to the properties of light and the ultraviolet catastrophe. So blue light or ultraviolet light is dimmer and vibrates at a higher frequency. The reason that we see more red light than ultraviolet light is that the latter takes so much more energy to make. But this left the scientists of the time puzzled and confused. Light was definitely a wave, which explained, for instance, shadows and the multicolored pattern on the surface of soap bubbles. Yet, as Einstein found out through the photoelectric effect, light was also definitely a stream of particles. This mystery about light became a proper battleground about the nature of reality. Thomas Young tried to resolve the mystery by designing an experiment, the so-called double-slit experiment, that would easily prove one or the other wrong. But he too was mistaken. His experiment proved unequivocally that light was indeed a wave and also a particle. What decided whether light behaved as a wave or a particle was a scientist's expectations, it seemed. When the scientist was looking for a wave, he would find an interference pattern similar to that observed in wave mechanics. When the scientist tried instead to find out which way the light traveled, which path the light took, or in other words, when he was trying to find out which way a single particle of light was traveling, sure enough, he found a particle. You wouldn't be able to find out how fast the particle was moving, but you'd be able to pinpoint its likely position as if frozen in space-time. Observation, in other words, seemed to take a snapshot of the particle in space-time. The deciding factor whether light was behaving as a particle or as a wave appeared to be the observer's point of view and expectations. Now, if this isn't shocking enough, what scientists found later was that not only light, but also matter acted in the same way. Electrons, the particles of matter, displayed exactly the same wave-like patterns displayed by photons, until observed more closely, until you ask the question, which path did this particle take in space-time? The particle appeared to be smeared and spread out like a wave, taking all possible paths at once. But as soon as you narrowed your focus, as soon as you asked which way the particle traveled, you would find that the particle definitely was taking just one path at a time. Which path it took, it seemed random. You just couldn't predict where it would travel. So if the experiment was designed in a way that allowed only two possible paths, the particle would travel through one or the other with a 50-50 chance. If it was designed to allow more paths, the probability would be lower for each path. In any case, you could never get a probability higher than 50%. But the path it took was influenced by the restrictions set by the experimental design. Because science had, up until that point, always been considered an objective method of inquiry in which the scientist was meant to be an external observer, you could see why scientists had trouble interpreting and accepting these findings. You see, if the way we look at reality changes the reality that we look at, then it seems there is no objective reality at all to look at. Reality, you could say, is in the eye of the beholder. To explain this using an analogy in our 3D world, imagine a spinning coin. A spinning coin is neither heads nor tails, or you could argue is both. But if you stop it with your hand, you force it to decide one way or the other with a 50% probability at random. The quantum world, like that coin, contains all possible outcomes until forced to make a decision by our observation in 3D reality. Then it collapses into one of the available options. The other face of the coin still exists. It has not disappeared into nothingness, it simply disappeared from our awareness. Just like it could be argued by the proponents of a sort of modified version of the many worlds interpretation of quantum physics, when you observe one reality into existence, you simply become aware of it. The other branch of reality has not been destroyed, you are simply no longer conscious of it. So reality, in other words, is fluid and malleable, but it appears objectively rigid and fixed because your consciousness is taking snapshots in space-time, and those snapshots are what make reality seem so, for lack of better words, so real. So to go back to the electron, it appears that the electron is spread out everywhere it could possibly be at once, and it takes up a specific position only when you observe it. There is no solid reality, only the potential for it. Things only become real when we observe them. Einstein rejected this interpretation with all its being, although he himself had unwittingly given birth to it. He was convinced that there must have been a better, more complete explanation. Yet, the double-slit experiment designed by Thomas Young was carried out over and over again, each time in more complex ways, which seemed to suggest more and more shocking implications, such as that at the quantum level there is no arrow of time. There is no difference between backwards and forwards in time. A positron is an electron traveling backwards in time. Things happening now can affect events happened in the past. By removing a detector after the particle has already been detected by it, we can make the particle go back to its previous wave-like status. If you're confused by this, welcome to the club. But let me reassure you, your confusion is not due to the fact that you're not clever enough to understand this. It's because these findings are truly mind-boggling and challenge all our accepted assumptions about reality. Einstein was just as confused, and that is why he refused to accept the interpretation of quantum physics that interpretation of quantum physics or quantum mechanics and consequently of reality. He thought that there must have been a hidden variable that we don't know about, which decides what path the particle goes through in advance, or whether it goes through any specific path at all. He argued, in other words, for an alternative view of reality in which the path taken by the particle is already decided and fixed before we decide to look at it. We simply lack the information, and therefore we assume that we have collapsed the particle into a specific state or another. He specifically was disgusted by the concept of entanglement of subatomic particles, discovered by Bohr and his colleagues in Copenhagen. But what is entanglement exactly? So, for instance, when two particles are produced together, in example, a photon goes through polarized lens and splits into two particles with opposing polarization. No matter how far apart these photons travel, when you observe complementary features of one of them, the other feature collapses into the opposite state. To use the coin analogy, imagine two spinning coins and imagine that they are linked in some way so that when you stop one on heads, the other coin immediately stops on tails and vice versa. It's bonkers, right? So Einstein claimed that the coins must be rigged in some way, as if linked by an invisible thread or something. Because according to his theory of relativity, nothing can travel faster than the speed of light, not even information. So Einstein argued that coins must be heads or tails from the start. When we stop one, we discover what their nature was all along. We just fill in the gaps of our knowledge. We don't cause anything to collapse. Now, the problem with this interpretation is, first of all, that it raises the question of free will. In other words, that our conscious decision to stop a coin at a certain point in time is simply an illusion. We never really had any choice at all. Secondly, Einstein's interpretation of entanglement has been mathematically disproven once and for all by Bell's theorem. But let me try to explain Einstein's point of view using another analogy. Imagine the two particles are like a pair of gloves. The two gloves are into different boxes, and we have no way of knowing where the right-handed glove is and where the left-handed glove is until we open the box and look inside. Now, the gloves were obviously left or right all along. We simply didn't know which was which until we looked at it and filled in the gaps of our knowledge. So when we open the box, the only thing that changes is our knowledge. To sum this up, according to Einstein, there is an objective reality independent of observation, yet our free will is an illusion. According to Bohr and the Copenhagen interpretation, our free will is real, but reality is not. Now, something's got to give. We either have to give up reality or our ability to make choices, our free will. Either we create reality through the decisions we make and how and what we decide to observe, or reality is already set and our decisions are made by something outside of ourselves, and we are delusional in our belief that we can freely make choices. John Bell resolved this conundrum with an extremely complex mathematical theorem, which I will not pretend to understand. I will instead use a well-known metaphor to explain it. Imagine playing a game of cards with a dealer. So you set the rule that you win the hand every time you get a different color of cards from the dealer. So when he tested quantum physics, John Bell found that the dealer won every single hand, time after time after time, to a point where chance could no longer be invoked. So every time the dealer had the same color of cards as you. So you now guess that the deck of cards must be rigged in a way that cards have been placed in pairs of equal colors. You get smarter and you now change the rule. And this time, with the same deck of cards, you decide that you win every time you and the dealer had the same color of cards. From here on, you get opposite colors every single time. And again, you lose every hand. So you change the rules again and decide that you win a hand every time you get a red card, say. But again, the dealer wins every single hand by getting a black card, by you getting a black card. So you assume, therefore, that the deck of cards is rigged every time according to the rules that you set. So you get even smarter. And this time you don't tell the dealer what the rule is until after the cards have been dealt. The unspoken rule is that you win every time you get a black card, say, but even this time you get a red card at every single hand, to a point where chance cannot be invoked. And at this point, you have to concede that the deck of cards could not have been rigged, as you were the only person who knew the rules of the game. There is no rigged deck of cards. There is no pre-existing reality, no hidden variable. Either there is no rigged deck of cards, no pre-existing reality, or if a rigged deck of cards does exist, it means that us telling the dealer the rules of the game after the cards have already been dealt affects the outcome of the game backwards in time. So we're faced now with the decision. We either have to give up reality or causality. You see, if the chain of events can run in both directions of time, backwards and forwards, there is no way of telling which is cause and which is effect. So it took 10 years for the scientific world to take notice of Bell's theorem's findings. It seems scientists just weren't ready for what that equation was suggesting about the deeper nature of reality. 10 years later, another scientist, Alain Aspect, found a way to put Bell's theorem to the test. He used polarized and tangled photons to do a quantum version of the card game. What Aspect found was that the photons features, for instance, polarization, did not exist prior to observation. The deck of cards was never rigged in the first place. And this was proven in an actual observation in the laboratory. It wasn't just a mere thought experiment. That's what I mean. So legend has it that Einstein once asked the question, does this mean that the moon does not exist before we look at it? This experiment seems to suggest that in some weird way, the moon really does not exist before we decide to look at it. Now, more recent interpretations of these findings, like the many worlds interpretation, for instance, suggest that while the moon still exists in some realities, in some branches of reality where a version of you or me does look at it, it doesn't in this one where we decide not to look at it. I know this will be confusing to some of you and disconcerting and upsetting to others. The problem with this conclusion is that it challenges our understanding of how the world works, our common sense, and on some level, even our sense of identity. Everything we've been taught throughout our life is that matter is real and the mind is only a tool that will enable us to manipulate matter through action, effort, direct contact, and force. Now, and in fact for over a century, science is telling us that matter may be nothing but a stubborn illusion, that it's possible that matter is just fluid and malleable, that is particles which behave like waves of probabilities are influenced by mind stuff at a distance and can even travel backwards in time to change the past. I know, this is a massive cognitive leap to take, and it might feel scary, yet it's not as bad, not as scary as being told that the future already exists and there is nothing that you can do to change it, no matter how hard you try. Think about it. That is what determinism, taken to its extreme, suggested. Giving up reality means that we can retain free will, that we are not useless puppets who think that they can change the world, they can change the future, but who are actually impotent. Giving up reality as we know it, solid, stable, unique, and unitary, means that a whole host of possibilities opens up before our very eyes, and we have the freedom to choose which one version of reality we want to observe, experience, and in a sense create. Ironically, Bell's theorem seems to give us no choice in the matter. If the deck of cards isn't rigged, then it means that there is no pre-existing reality, that reality only appears when we decide to look at it. The reason that matter acquires certain physical, measurable properties when we look at it is not because we were previously unaware of something that was there all along, but because before we decided to look at it, that property did not exist. I can't stress this enough. This is not some flight of fancy. This was mathematically proven. Reality does not exist before you decide to look at it. So we are not some insignificant puppets who came onto the scene of the world by chance. We appear to have observed our own existence into reality. Let that one statement sink in. That is why Richard Feynman stated that if quantum physics doesn't shock you, then you haven't fully grasped it. So this is it for today. I intend that this podcast helps you to shape reality in the most pleasant, fun, easiest way possible in the direction of your dreams. I intend that it helps you to stay focused on your wishes and desires, knowing that if you do so, you will see them harden into fact. Like that wave which collapses into a particle in space-time, or like that new branch of reality which opens up before your very eyes. So if you've come this far and have enjoyed this podcast, please like, share, subscribe, and hit the bell option so you can be notified of my future content. In any case, thank you for listening. Have a wonderful, creative, awakened, dreamlike life.